Okay, so we're going to continue with our talking on distributions. Previously, we talked about the geometric and the binomial. Now we're going to talk about the normal. And the normal is a really important theoretical idea used in statistics to model data for large populations. And when I say it is important, it ultimately, and you won't see this until next semester, is probably one of the most important, if not the most important concept in all of statistics. But I'm jumping ahead a bit. So, what do we know about the normal? First off, the graph of the normal is symmetrical and bell-shaped. Now, I want to caution you. Just because a graph is symmetrical and bell-shaped does not mean that it is normal. Okay, you can have symmetrical and bell-shaped curves, and they're not normal. So you have look for the word normal in the equation or in the problem stem. We will almost always let you know that it's normal. At least for the time being, or at least for this semester. They're normal based on a particular mean and standard deviation. Now they have an awful formula, and I'll show you the equation for it in just a moment, and we'll look at that, but you're not going to have to memorize it or use it. Theoretically, the graph extends from negative infinity to positive infinity, theoretically. And below, I have some graphs of normal distributions. But they have different standard deviations. Now, they do share the same mean, because notice they're all centered on the same place. Now, just truthfully, there's an infinite number of means and an infinite number of standard deviations, so they could be all over the place. But for my purposes here, I have them centered on the same mean. So if we look at this, we can sit there and go, hey, you know what? This is shorter and more spread out, but it still goes all the way to negative infinity, all the way to positive infinity. So we have a little bit of Buzz Lightyear to infinity and beyond. And the same with this one here, and the same with this one here. So this one here has the smallest standard deviation. This has the smallest standard deviation. It has a small standard deviation of 0.5. This one has a standard deviation of 1. And this has a standard deviation of 2. They still, all of three of them go to negative infinity to positive infinity. It just happens that this one is steeper and narrower, and this one is larger and fatter, or wider and fatter. Now that said, the area under the curve for all of them, and you probably want to write this down, area under the curve, so area under the curve is always 1. Always 1, just like what we talked about before. So it's basically a valid probability distribution going from negative infinity to infinity. Now I'm going to show you the equation of it. So this is the equation, and don't worry, we don't have to fool with it. AP Statistics doesn't have to fool with it. If you went on to Calculus BC or you went on farther in statistics, you would, but we don't do it in AP, we don't do it here, but I just kind of wanted you to see it. And one of the things that you'll notice is we have the standard deviation listed in 2 places. And we have the mean right here. So here's our standard deviation in 2 different spots, and then we have the mean. And once again, I just wanted to show you the formula. You won't even have to write it down, but that's what it looks like. Now, there is a different normal curve for every standard deviation, and there's a different normal curve for every mean. So there's an infinite number of combinations, but they all will follow this particular equation. Any bell-shaped curve that doesn't follow this equation is not normal, all right? And you're like, well, why is it important? Well, we're only going to talk about it briefly. We'll see more of why it's important next semester, because ultimately we're going to find that any distribution can be turned into a normal. We're going to see that next semester, and it's very easy. But right now, we're just going to talk about curves that are already normal. And the normal distribution describes many things in the world, much like SAT scores, ACT scores, height, weight, for that matter, IQ is all described by the normal distribution. All right, and one other thing to talk about the normal distribution, even though it goes from negative infinity to positive infinity, almost all of the data will fall within plus or minus 3 standard deviations of the mean. So basically, if we were to number these off, we'd go, okay, 3 standard deviations this way, 3 standard deviations that way. That's almost all of the data, okay? Even though it continues on, And that just means when we get really out here, far out here, that's really rare. Really far out here, that's really rare. Okay? All right. So I'm sure at this point you're probably thinking, great, an infinite number of curves, an awful looking equation. How am I ever going to learn all this? You know, it looks like I'm going to need to be a student aide, or can I go see the counselor? Don't do that type of thing. You can do this. Trust me, there's a lot of groundwork to lay, but when we actually start doing the problems, which will be in the second and third video on the normal curve, you're going to see this isn't so bad. So we're going to introduce something called z-scores. And actually, we talked about z-scores earlier, and I'm going to write it up here, even though it's further down on the page. And z equals x minus mu over sigma. That's the formula. And basically, we have our mean and our standard deviation and an individual value. So a z-score is essentially just a ratio that says how far a single data point is from the mean relative to all the other data points. That's all it's doing. It's kind of giving almost like a percentage. But I wanted to talk to you about the normal, couple more things. First off, 68% of the data are plus or minus 1 standard deviation from the mean, 95% are plus or minus 2, and 99.7 are plus or minus 3. And previously we said almost all of the data is within 3 standard deviations. And this shows right here that it's plus or 99.7%. So almost all of it. Basically, there's 0.003 out in the tails. That's a really small amount. Okay, so back to the z-scores. So on a z-score, you're like, well, what are they good for? Well, they are a scale. And basically, as a scale, they tell you you can actually compare different distributions. And if you think about this, you can sit there and go, you know what? I know so-and-so has a different teacher than I have for the same class, and their class is so much easier. Well, this is a way that you could actually compare how one student does in one class versus another class. And as a result of a z-score, we're going to be able to convert all of the infinite number of distributions, of normal distributions, into a single distribution. All right? Now, here's the z-score formula that I mentioned. Next semester, we'll look at something like that, but don't worry, it's next semester, and by then you're going to go, oh, this is no big deal at all. So, once again, we can convert all the distributions into all the normal distributions into a single distribution, and that single distribution is known as the standard normal. And with the standard normal, we are plus or minus 1 standard deviation away from the mean, which is, we look at this and go, you know what? There's 68% of the data right there shaded in that blue shade. Plus or minus 2 standard deviations is 95% of the data, or it's about 95, it's not exactly. And plus or minus 3 standard deviations, so basically out here is 99.7% of the data. Now remember, this goes all the way out to positive infinity and negative infinity. And if we went all the way out to there, we'd have 100% of the data, but you can't go to negative infinity, you can't go to positive infinity. So basically, this right here, the 68, 95, and 99.7, and you actually do need to memorize those terms. So plus or minus 1 is 68%, plus or minus 2 is 95%, and plus or minus 3 is 99.7%. All right. So turns out the 68 and the 95 and the 97 has a name, and it's called the empirical rule. Please make sure you memorize those percentages. And remember, 68 plus or minus 1, centered on the mean. Plus or minus 2 is 95, centered on the mean. And plus or minus 3 is 99.7. And this is all known as the empirical rule. All right? All right, one thing to caution you. The empirical rule, now listen carefully, only applies to normal curves. It applies to all normal curves, not just the standard normal. It applies to all normal curves, but it does not apply to anything else. It can only be used for the normal. Do not use it for anything else. All right. So once again, one of the things I think is really awesome is I can take the infinite number of normal curves and convert them to a standard normal using z equals x minus mu over sigma. So that simple formula will convert the infinite number of normal curves to the standard normal. All right. Now, one other neat thing about the standard normal has a mean of 0 and a standard deviation of 1. Always. The standard normal has a mean of 0 and a standard deviation of 1. And you go, wait a second, I thought you said there's an infinite number of possibilities for the mean and an infinite number of possibilities for the standard deviation. And that's true for normal curves. But for the standard normal, the one that we convert everything to, there's only this, the mean equals 0 and the standard deviation equals 1. Now, I'm going to tell you, that's pretty awesome. And if you're not clapping yet, I want you to think of one more thing. The calculator does a lot of this work for you, almost all of it, actually. So you can do this. I know you can. Now, I did not read every single line of this because I know that you can. Please go back and read all the notes. There's some important information in that. Thank you.